Hi, this is Stephen Brown from Red Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language, and this is meant to be the overview for Stallings Chapter 10. In Stallings Chapter 10, one of the things we'll take a look at is multiplication of binary numbers, and for signed binary multiplication, we'll look at Booth's algorithm. The other thing we'll look at in the chapter, which we're going to revisit in Irvine Chapter 12, is floating point notation. And one thing that will be pointed out is the IEEE 754 standard for floating notation, which has four pieces: the sign, the biased exponent, the significand, and the base, which is assumed to be 2. So we'll look at the 32-bit notation. Later when we get to Irvine Chapter 12, we'll look at the 80-bit notation. One of the issues that can happen with floating point notation is you end up with an underflow. So it's like there's the smallest decimal number. Let's just think of positive for a second. Think of like 0.0000001, and it can't represent something that's smaller than it. And so what sometimes happens with the math is we actually can end up with an underflow where the value can't be represented because it is too small. One of the things that should have been pointed out in your Java course is that when you're comparing doubles, you really shouldn't use the equals equals. What you really should do is take one, subtract the other from it, come up with the absolute value, and if the difference is less than an acceptable allowable deviation, then you say it's meant to be the same. But again, we'll revisit floating point in Chapter 12. Well, I don't know if you guys learn multiplication this way, but the way I learn multiplication is, if we're trying to multiply these two 3-digit numbers, I would take 2, multiply it by 309 to come up with the 618. Then I would take the 4, multiply it to 309, and then in this position would be the 1236. The 1 times the 309 would be in this position, and there's the 309. And so what we have is, and we may not have identified it as this, but these are partial products. And then we would add those partial products together to come up with our number. And what I just want to do here, there's a reason for this, is I want to show it's the same multiplication but reversed. So the 9 times these numbers to come up with the value. But when we do 0 times this, we got to make sure we hold on to the 0 because we need this place, because the next one, the place is going to be over here. And then we have these sum of products, and we add them together to come up with our number. One of the reasons why I wanted to point this out is that something, if you did multiply this way, you were shifting in terms of the numbers. Well, imagine when we're dealing with binary numbers and we're doing multiplication. So 0 times all of this, well, that's just 0. We need to shift over 1. 0 times all of this, well, that's 0 as well. 1 times all of this, that's the 0011. 0 times all of this, then there's the 0. So we have a partial products, and we need to sum them together. And what happens is when we do the summing, we actually have the 0 down here. The reason why I added this extra 0 is that if we need to do a carry, we want to hold on to one more carry bit because it can have a difference in how large the number is. So for unsigned binary multiplication, this process can be used for unsigned numbers. But for signed numbers, we need a different process. And so suppose this is one of the numbers we're multiplying. This is the other. So we have our M and our Q, and we'll have these A as being another register. So M, Q, and A are registers. And what this Q minus 1 is meant to be is at the point where we're doing a shift, it's meant to take the value off to the right. Oh, I think I'm off a slide. Yes, this one here. So if we're going through the process, if we're doing Booth's algorithm, we would put M in one register, we would put Q in the other. Now in this case, this is positive, this is negative. So our Q, and this is just the way that this was set up, this is a negative number. The result we should get is going to be negative. We'll initialize, our A will be 0, and then our Q minus 1 will be 0. Well, in Booth's algorithm, each step, so the first step that we have, we're dealing with these initialized values, but each step we're going to look at this rightmost bit in Q, which we refer to Q0, and then the one that's going to hold the shift, which is the Q minus 1. And from looking at, and if you think of those two bits, there's 4 possibilities. 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 possibilities. Well, depending on what those bits are, we will do one of 4 things. If it's a 0, 1, we're going to add M, so the M that's here, we add it to A. If it's a 1, 0, we're going to subtract M. And the way you actually can subtract M is you actually can add the complement. In both of those cases, after the adding of M or adding of the complement of M, a shift is done where the bits are moved to the right. If it's 0, 0 or 1, 1, only a shift is done. Now in this case, because of the 1, 0, that is where, oh, I'm sorry, it's the next slide. I'm jumping ahead. Here we go. So there is the adding of the minus M and showing that's been affected. So that is when we did have the 1, 0, this first piece was adding of the minus M. The shift, I'm going to show in the next slide because I was having an issue when I tried to put it in this one. But here are the bits the way they were laid out. And I'm not showing here the Q minus 1 because it's about to get overlaid. But what will happen is the rightmost bit will shift for right here. These bits will each shift right 1. This rightmost bit will shift into here. These bits will shift over 1. And then we're going to have a leftover space at the end. We've got to fill it with something. So that rightmost bit moves over. These bits move over. This bit moves over here from the A into the Q. Those bits move over. And then to maintain the sign, whatever the leftmost bit is here, we'll make a copy of that for bringing it in. So if it's a 1 as it is here, we bring in a 1. If it's a 0, we'll bring in a 0. And so, by the way, there's going to be 3 videos that are going to go through this example. And I also have a PDF of the end result of it. And so what we just went through here on the prior slide, adding in the minus M and then doing the shift to the right, the way the bits are set up here, that's the end of this step 1 here. So 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, and then a 1 in the Q minus 1, the 1 in the Q minus 1. So this is showing what the end of step 1 is. If we have 6 bits, you would do 6 steps. If you have 32 bits, you do 32 steps. So there's going to be several Booth's algorithm examples, and there's separate videos for each one. That's enough for an overview. Oh, what a train.